focus is on the 10 degree C rise, general rule of thumb. I think it'll become more evident that, that methodology has a lot of holes in it, and it's not a good guideline for people. And the way I'm approaching it is, let's look at the charts in 2221 and look at what the power dissipation in those traces were. Then let's look at the charts in 2152 and what the increase in power using 2152 is. And just looking at those power losses sheds a lot of light on what a 10 degree C rise really means. The 10 degree C rise concept is really only good for a given technology. And it's hard to identify what that really means until you look at your own specific design. Whether it's a small little tiny board, that's in some application, or a very large board, that could be 30 some, 40 some layers and 3 by 5. How does anyone expect that a small, tiny little board and this monstrous board should have the same 10 degree C rise design criteria? It just doesn't make any sense. When I first started working with the design standards group, what I wanted to do is design for power dissipation and manage the power losses in the traces and conductors as they are, as a total. When you turn on all of your circuitry, understand how much power losses you have in your design, and have a budget just for the conductors. And then, when we started embedding resistors in boards, include those too. All of the losses in the board, that's what needs to be managed. And the temperature rise is going to be a function of how that board is mounted and how much copper is in that board to help spread that heat. And so to say that you've got a 10 degree C rise is pretty meaningless.